Synchronous Motors, Introduction, Applications, and Operation. In this presentation, we're going to be looking at specifically the parts that make up a synchronous motor, why synchronous motors are used, how synchronous motors work, and finally, torque angle. This is an example of a simplified synchronous motor. Really, all it is a skim motor with a wound rotor in the middle, but a little bit different. You'll notice that it's simply a single winding in the middle, and instead of it connecting to a resistive external bank, it's going to connect to a DC source. The wound rotor looks very similar to that of a wound rotor motor. We have slip rings and carbon brushes, but again, notice that we only have 2 slip rings, and that is because we are only applying DC voltage to the windings on the rotor, as opposed to 3 resistive banks to 3 separate windings. All of the items together look very similar to what we've looked at in the past on skim and wound rotor motors. The center has 2 brushes that contact 2 slip rings. The 2 slip rings connect then to the windings on the rotor, and the stator looks exactly the same as both of the previous motors we've looked at in the past. One of the additional features that's a little bit different is something called an Armature winding. An Armature winding is very much like an induction motor squirrel cage. It's simply smaller, and it is able to carry less induced current. Now we'll talk about why a synchronous motor even has this. We get a better image of it here, where we can see the actual individual Armature bars. Although they call it a winding, they're really bars, and they're all connected around the rotor. So essentially what we have is a mechanically connected series of bars that are short-circuited at both ends in exactly the same way as a squirrel cage would on a skim motor. Now, synchronous motors are very rarely manufactured in smaller sizes, and when they are, they would be identical in visual form to standard skim motors. You wouldn't be able to tell the difference between the two. The one on the left is a synchronous motor. The one on the right is a skim motor. More commonly, though, synchronous motors are manufactured in very large sizes in higher voltages, so several hundred horsepower. These are 2 examples, one with a cutaway, and the larger section on top is a form of a cooling mechanism for the motor, so pretty substantial items. The main reason that synchronous motors are used, or I should say one of the reasons, is constant speed can be maintained regardless of mechanical load that's applied to the motor shaft. If we compare a skim motor against a synchronous motor, a skim motor will have a nameplate RPM. At no load, it'll be a little bit faster than nameplate. At full load, it should be right on nameplate speed. And when it's slightly overloaded, the speed of the shaft should slow and therefore be slower than the nameplate rating. By contrast, a synchronous motor will have a nameplate speed that's actually identical to the synchronous speed of the stator. At no load, it'll be 1800 RPM, the actual rotor spinning. At full load, it'll be 1800 RPM, and if slightly overloaded, it will again be 1800 RPM, and because of that, it's seen as a constant speed machine. Now, there's lots of different applications for a machine like this. One that comes to mind and that we have out in BC is pulp and paper mills. They usually involve a series of rollers and presses that take the wet fiber material out of the moisture-laden buckets and trays, and it slowly presses down to a fine, thin sheet where all of the moisture has been removed as it goes through a series of different additives and drying processes. Now consider, each one of these rollers must be turning at exactly the same speed because what is woven around each roller, and you can see with the black line that sort of goes through the whole system, is a single continuous sheet of paper. If each roller was not driven at exactly the same speed, this continuous paper sheet would tear or become backed up, causing significant delays in production as that broken or ripped portion of paper would then need to be threaded through all of the future or preceding rollers. If all the motors are the same, they could be synchronized to turn at the same speed due to the supply frequency of the facility. So primarily how we are going to synchronize a motor has to do with the supply hertz. The other reason that we use synchronous motors is the power factor of the motor can be controlled so that it's either lagging, unity, or leading. Now, what that means, if we contrast it against a skim motor, we all know that a skim motor will operate at a lagging power factor. And we can see the green motor there, 0.8 lag, 5 amps FLA, and we know that the current value will change. On a synchronous motor, the power factor is typically rated at unity. And that means for the same amount of horsepower, a synchronous motor will actually draw less current. At no load, we would see less than 3 amps, probably not 3 amps. Full load, we would see 3 amps, or the rated value, and slightly overloaded, we would see a little bit higher than 3 amps. So draws less total current. There's another type of synchronous machine, which is called a synchronous condenser. And as you can tell, visually, the only difference is that there is no shaft. There's no shaft coming out, which means it doesn't drive a mechanical load, and its entire purpose is to simply provide power factor correcting VARs. Since we can adjust the power factor up into a leading zone, we can use leading power factor or capacitive VARs. And it means that it's now an infinitely adjustable leading VAR bank or capacitor bank, if you want to think of it that way. Here are the surcharges we're attempting to avoid with power factor correction. Remember, this has nothing to do with the total amount of in-phase current you're drawing, but rather how much out-of-phase VARs are you requiring from the supply authority. By putting in power factor correcting capacitors or a synchronous condenser, we are lowering the out-of-phase inductive VARs that BC Hydro is providing and reducing our surcharge. Here's an example of a synchronous condenser just plugged straight into a motor control center, which is simply a purpose-built box that has a whole bunch of motor starters inside individual bays. Now, the basic operation of a synchronous motor is actually quite simple. We have a stator that connects to three-phase in the same way that it would on a skim motor, and we have a rotor that connects to a DC source. This is a more simplified version of what's occurring inside the synchronous motor. The green is the stator, the red is the rotor. When we energize the stator, a magnetic field is set up. When we energize the rotor, a magnetic field is also set up. And what this then means is that since they are both creating a north and a south pole, there will be an attractive force between these opposing poles. And since it's on two separate locations in the machine, the rotor being able to move, it's going to lock the north and the south of each of the rotor and the stator fields. They're once locked together, the motor is considered synchronized. And there is now no difference between the stator and the rotor speed. If we were to take a look at a synchronous motor and remove the rotor from this motor and energize the exterior stator field, we would see this rotating magnetic flux that's set up. The speed of this flux is calculated by knowing the poles and the frequency of the supply that the three-phase has been generated with. If we were to look at the coil inside the rotor, when I energize it with DC, I have a constant DC or static magnetic field set up in the coil. So let's say we start this motor with full voltage, three-phase. Notice that it takes some time for the rotor to pick up speed. And what's happening here is when the motor is started, the armature winding is what brings the rotor up to a fairly close speed to the synchronous speed. The armature winding is a short-circuited series of bars and rings, the same as a skim motor, which means since there is breaking of lines of flux, there is voltage induced into the armature, which means there is current induced, which then results in torque being developed. Without the armature winding, this motor would be unable to start. Once the rotor is turning at a low percent slip, from 1 to 3%, that's when we energize the field coil with DC voltage. At this point, once we have that DC field energized, it will immediately lock into the synchronous rotating magnetic field. At this point, there is zero slip that is occurring, and the rotor is turning at exactly the same speed as the stator, therefore synchronous. The synchronous speed of the stator is now the same as the rotor. And rotor speed will not change as mechanical load is added to the shaft of the motor. So a rotor that is synchronized is locked with the rotating stator field. Starting a synchronous motor takes a number of steps that all must be done in the right order. Let's just review them. The stator is energized with three-phase AC. The armature winding develops torque due to the breaking of lines of flux. The motor is started with no mechanical load. Obviously, it starts to rotate due to the armature, and when the speed of the motor is between 1 to 5 or 1 to 3%, the DC rotor winding is energized. The rotor synchronizes to the stator field, and the percent slip drops to 0. Mechanical load can now be increased on this motor, and the speed will not be affected. When the rotor is synchronized to the stator, there's an attractive magnetic force that locks it into place that we have been discussing. Now, it's sometimes easier to think of this as elastic bands, the connection between the north and the south poles of the stator and the rotor. The deflection from center between the rotor and stator pole is called the torque angle. Now, the reason that we like to consider this like elastic bands is that, well, you can imagine if I increase the amount of mechanical load too far, the torque angle will actually get quite large. So on the left, we see synchronous motor, no load. Torque angle is almost 0, not quite. On a synchronous motor that's full load, the torque angle is greater than 0. Now, the more mechanical load that I add to this rotor, the greater this torque angle will get. Increasing the mechanical load increases this torque angle, and eventually the rotor will fall out of synchronism. And the way you can consider that is that the elastic bands would snap. They've been stretched too far. The value of torque that will cause this in a synchronous motor is called the pull-out torque. If a synchronous motor falls out of synchronism, it will immediately stall. Now, this is due to the armature windings being designed to start the motor only, not to operate at full mechanical load. The DC field coil must be de-energized. High stator current can damage the motor, same as a skim motor. To resynchronize, the mechanical load must first be reduced, and then the DC field winding re-energized. So you can't just resynchronize this motor if it has been stalled under load.